So, how you guys doing today? Good, perfect. You guys all had a good spring break? Good, perfect. All right, so I hope you guys remember what we did before spring break. So I'll give you one question. You can try. Okay. This one. So you can try to this one. I'll give you 1 or 2 minutes. And this is kind of something we did before the spring break. So you can try your best to find out the answer. Okay, this 1 or 2 minutes. Okay, 30 seconds, and we'll do this together. But just try to remind yourself about what we did before spring break, and then I'll move on to the next chapter. Okay, all right. So if you look at this one over here, this one will grab this one over here, right? So the possibility is either you can have, so think if you, here, so if you get this one, okay, and then either you can put it here or here, okay? That means either you can have carbon cation here or here, okay? But this is better because this carbon cation will be much more stable than this one, because this will have only primary carbon cation here, but this will be what? Secondary. So there are 2 orbitals on here. So then you're going to have this, okay, intermediate, and then this one becomes negative charge, pair electron donated here once they taking the hydrogen on itself, and then it goes to here, okay? Then you can say, okay, because I'm not gonna show you the implied hydrogen, okay? So if you do this one, meaning you had a really good understanding of chapter 7, okay? And then this is actually not the right answer. Because there's one exception. I talked very last part of chapter 7 was hydride sheet. You guys remember this? Hydride sheet. So, okay, if this is better than this position here, right? And then think about there's a implied hydrogen here. And if you can move this one to here, they'll be even more stable because it's actually more substitute in this position here. So this hydrogen and a pair of electron move to here. So that makes this one. So this is exception because this is where you can have even more stable, possibly carbon cation position. And then this comes in and finish the reaction. So they actually become, so the correct answer is this one, okay? So it's a good reminder, right? So this is just few exceptions that you need to know if there's a case. So if I give you just this, right? If I just give you this one, obviously you just need to do this one, okay? But there was exception because there were possibly even higher stability of the carbocation, you may need to do hydroxy over there. But in this normal case, it's just this one. Okay. Does it make sense? Okay. So normally you don't have to do the hydroxy, but just in case of this type of very exceptional case, you might have to. Does it make sense? Okay. So don't. I'll do this again, obviously before the exam 2. But we have some more time to work on this, so we can practically even do exercise preparing for the exam 2. All right. So the chapter 8 is about alkene. But we're gonna do lots of different types of the chemical reaction with this one. Okay? So maybe you have this double bond summit between your carbons there. You can make some alcohol compound. You can sometimes make halide. Sorry. This is a halogen. So normally when I put X there, it's a halogen element. So you can see fluorine, chlorine, bromine, and iodine and so forth. The halogens are this X symbol right there. Or sometimes you can do dihalide compounds. So they can all come. This one, you can also make two hydroxy group on those two carbons, which we call diol. So diol simply means two alcohol. O is OL is the last two syllables of alcohol, and di means two. So you can mix or diol. Sometimes you can mix some epoxide. Okay. Something like a cyclic portion of your compounds too. There's some, and yeah, this is the di. Okay, so there's so many things actually. There's even more we can do with this one, but there's very few few products you can make from the alkene. This is what we're gonna talk in chapter 8. Okay, so eventually we're gonna talk about certain part of this chemical reactions will be classified as in either oxidations or reduction, and I'll tell you how we can do this in very detail soon this weekend, probably early next week. All right, so first of all, you can also try to make some alkene formation with the elimination reaction. Okay. You guys remember this is one type of a chemical reaction you can do: addition, elimination, rearrangement, and so forth. This is the how you can prepare the alkene from the alkene. So one example I can give you is this one. If you have this is a bromo, cyclohexane, right? Okay, it's bromocyclohexane, and you can treat it with a certain kind of strong base. Okay, so it has maybe with the alkali metal. So maybe one good example you can try is potassium hydroxide. Okay? And then you can try to put it in certain organic solvent like ethanol, which is common organic solvent over here. Here's the one thing you can do. So even though you don't see it here, you know there's a hydrogen over here, right? Okay. So if you look at this one actually here, this is a strong base, meaning they're gonna all fully dissociate like this. Okay? So in this case, if you look at this hydroxide anion, this is what it looks like. This is a 1, 2, 3, 4, 5, 6, 7. So this is group 6, but it has now what 7 valence electron. So it has a -1 charge. It has one more electron than it need to be neutral. So now a pair of electron actually goes to this one. Okay, and then this one. So you see there's a pair of so you guys know what the covalent bond is, right? This is just the area we can share the pair of electron here, and then once one of the lone pair attacks the hydrogen here, and this one goes to here, and that makes enough push to this one to leave. Okay, so and in this case, so you're going to have this. Does it make sense? So then you're going to have this one, and this one, and this one will. Okay. And now you have another electron donated here, so it becomes double bond. Makes sense, right? So from I don't know if you guys remember this from chapter 8. I highly recommend you go look at the quick review on the very last 2 pages of your each chapter. That show you all the summary of the chemical reactions that's specifically taught in that specific chapter. Whenever I do this, you don't have to know the mechanism. So I show you this will move here, here, and here. You don't have to know. Only thing you have to know is if there's the halide with the cyclohexane with a strong base, it can show some dehydrohalogenation, meaning it remove these two to make alkene. Okay, that's all you need to know. Does it make sense? So you don't have to know all the mechanism. It will not be on the exam. Only thing you have to know is the yeah. You just need to know what might be the outcome based on. So what happened here actually is we eliminated these two. This halogen here, hydrogen. So we call this dehydro, meaning hydrogen, and halogenation, meaning it's just a halogen. Makes sense, right? All right. Okay, the next is this one. Okay, sometimes you can treat it with some alcohol compound with the actually very strong acid solution here. With this is a kind of also common organic solvent. We call this tetrahydrofuran. This is what it looks like. If that is happening over here, you actually can assume there will be there's also okay. So if you have this one here, this is a strong acid, right? So you're gonna have lots of this hydrogen cation. So what happens to this one is this one will actually, so there's a 2 lone pair. So this is actually what it looks like, right? So if you have a 2 lone pair over here, okay, and they grabs this one because this is the lone pair it'll take something that is positive. So what it happens to this one is this one. Okay, so the positive charge goes on here. Okay. So then to be so this you can live this is like a water. This is a water group attached to this here with a positive charge because this one just grabbed the one that is positive charge. So most likely whenever you see this one, this kind of water type of groups, it will be actually you'll see this many times in order one. So whenever you see this one, you can assume this will leave, or either they're going to detach the hydrogen to be stabilized. So in this case, they're going to leave by just so this is the positive charge. So oxygen wants to take the pair of electron here, so they can be neutral like this. So they can be because they're breaking bond here to just getting these two pair of electron, one pair of electron to there. So they can be neutral. Okay, so it'll be okay. Makes sense, right? Good. So okay, once again, you don't have to know the mechanism. Okay, I'm just doing this for your the better understanding, but you don't actually have to. Yeah. You just need to know what might be the outcome. That's all. Okay. So the if that is the case, now you have a water just gone, and you have a carbocation position now here, not on the water anymore, and then this water here. It also has a two lone pair there, right? They grab this one, and this one goes to there. So they can be, this can be gone. Okay, so they're grabbing. So if this grab this one, they become hydrogen cation. So now positive charge over here, and then this one goes up, breaks. Okay, so technically you eliminate what? This hydroxy group, hydrogen, together what? Water. So you actually remove the water from here using strong acid and some water with a common solvent, organic solvent molecule like tetrahydrofuran. So so this is also elimination, so you can have your alkene compound prepared. Okay, makes sense, right? We good? So, like I said, you don't have to know all the detailed mechanism. You only need to know, if you have a strong base with the halo compounds, or some the alcohol compound with the strong acid, they will do the elimination. So then possibly they're gonna do some alkene compound formation. Okay? That's all you need to know. So this is the water is being removed, so it's dehydration. It's literally dehydrated. Make sense, right? Yeah. Don't worry about the mechanism too much. Once again, I'll keep saying this so many times this semester. Focus on the product, what product you can expect from the chemicals. So anyway, so let's talk about the first type of chemical reaction with the alkene. If you have alkene prepared, the first one is halogenation. Halogenation over here. So what you can do is, if you have this alkene compound over here with the chlorine. Here's something about the halogenation. So this is also same for all the other chapters from chapter 8. That we normally use halogenation for those. Okay. We don't use anything below the iodine. That's not so common and not so useful, because even when you get to the iodine, it's not very reactive. Not so much reactive. Okay. Problem for the first one is too reactive. Okay, so most likely whenever you do the halogenation on any compounds, not even just for the alkene, but alkyne and other compounds. We mainly focus on these two. There's special way to make this happen, to make it less reactive, just make a fluorination, but not so common. And iodine, because of the size and the tendency of the chemical property, they were not so reactive, so you have to have very special catalyst to make it happen. But these two are pretty common and also, relatively speaking, quite somewhat adequately reactive to the compound. So this is the one that we normally gonna focus on, the halogenation, and not just for this one, but everything else. Okay. So anyway, so if you do this one, you can actually see this type of the halogenation here. This is quite okay. But if you guys actually remember what we learned from chapter 7, I'll show you the mechanism here, and you can say what it possibly happened. So if you have this one here, okay, like you guys remember this one here, right? Okay, if you have this, okay, let's try to do this one instead. So maybe this has a similar mechanism. So this will work this one first, okay? So they have this one, okay? And then this one later comes here because it's now negative, because now the pebble went to here, now it goes to here, so that makes this one, right? So maybe we can apply the same. So maybe the earlier chemists were thinking about, oh, they may do the same job. So they do attack here, okay? And then maybe this pair goes to here, so they become H charge. So this will be here, and now it starts here, okay? So then they have this one, okay? All right, so this might be the mechanism, but don't copy this one. I'll tell you why. So we actually use the same mechanism we tried in the chapter 7 for this halogens. But here, this is actually not possible, okay? Because I'll show you one. So yeah, I'm just showing you the wrong mechanism, okay, to explain some ion, okay, which is this one, okay. This is a bromonium ion. We find this one, okay. So the mechanism, the correct mechanism is actually this one. So if you have cyclopentene over here, what it happens to this one is they attack this one here, and as you know, they all have I didn't show you, but it should have 3 lone pairs on each anyway, because bromine, all halogen has a group 7. It should have a 7 available valence electron around it. So it has a 1 bond there. So it should be 1, 2, 3, 4, 5, 6, 7. Meaning it should have each bromine in this form had to have 3 lone pair. So then they're actually going to attack here. So what it happens to this one is they form like, now it's gone, this one. Okay, so this is the, so do you see this, the bromine cation are bound to these 2 sides, which is R group, your Q group like, and that is R2. That's what it stands for, R2, bromine with a plus charge, because they're making Devon over there, right? So this positive charge bromine are kind of live in this compound is like a cyclic shape. So this is what we call bromonium ion formation. Okay? So what is so special about this one is the now it detach the one of the pair electron, because think about it, halogen wants to be always negative, well, at least neutral. Then once they form the bromonium ion, which is obviously you can think as very unstable status, right? It should be very unstable. So then they should automatically, immediately break one of the bonds here. So they can be here, but at the same time, on the other side, with the negative charge coming into that position. Because once you break this one here, it becomes carbocation, but this will become neutral. So they kind of hang here, and then coming into here. So then the problem was, whenever you do this one, they're always going to put each bromine in the other side, not on the same side. And this is where the scientists find out, oh, this might be the reason why. Because if it was the same mechanism that we try in chapter 7, it should also show you what? This one is wrong. They're on the same side, but this was not found. So this is only possible when they form the bromonium ion. So because of the previous bromine was initially attached from this bromine element form, making something like the structure and the down there. That's why there's another bromine with a negative charge couldn't come onto the same side because of there already something there. So they only have to come on the other side, which is open space. So they're always going to be opposite side. Then it explains it well. Okay, makes sense, right? So it means it's always coming onto the opposite side. So we call this anti-stereo chemistry. Meaning they're always going on to the opposite side because it's anti. Okay. So this kind of explains it too. And actually there was a so this is only making addition on the stereochemistry addition. So does it make sense? Does it make sense? Alrighty. So can I move on? Or do you want me to give you another example? One more. Okay, sure. One more. So if I give you this one, okay, this one with maybe this one, can you guys do maybe this one real quick? So the one tip I can give you is this one. Think about there's also implied hydrogen on this side. So once again, you don't have to know the mechanism. You only need to know, it should show the anti-stereochemistry product. Then you can actually estimate what product one may be. coming from this halogenation. Okay, so compare this one to yours. Okay, so if you do this one, this will become okay, because it has to be on opposite side. So this is one going up, going front to you. This is going back. So if you put the this one will be wrong answer, okay? Because this has to be anti-answer. So normally we don't show the what? Hydrogen on the paper, right? So this might be make sense, right? Okay. All right. So let's move on. Okay. All right. So the next one is what we call halohydrins formation. So halohydrin formation is usually if you have once again some double bond summit in your compounds, you can either do with the X2 over water. Okay. So X2 over water simply means once again this X represent the halogen elements. So it could be, but maybe not so much with the fluorine and iodine, but bromines or the chlorine. Okay. So and then water over here. Okay. So it's pretty much the same. The reason why we did the halogenation first because it shared a very similar mechanism. This the halohydro formation here. So what happens to this one here is, for example, if you have this trans-2-butene over here, maybe you can switch this one to, once again, bromine, okay? and the water here. Okay. So what happens to this one here is they grab also one of the bromine, okay, in the molecule, and then they're actually going to form bromonium ion again. Okay, so if that happens here, so there is some hydrogen here, right? So if that happens to here, have okay. Makes sense, right? Because you guys did this, it's pretty much the same here. And then now this, the water comes in on, obviously they can approach on this side, right? So they already have a bromonium ion formed there. So they're actually going to get to over here, okay? On the other side, right? And they now breaks it in this one, okay? So then they're going to have this one, okay? And then another water will pick up this one to be this one, okay? So then what it really happened was, then you're actually going to have this one. So if you rewrite this one, that's what happened. So halohydrin formation. Makes sense, right? It's very similar to what we did, but it has to be on the opposite side. Okay. All right, so can I move on? It makes sense, right? So only the difference is the water. Instead of the halogen with a negative charge, they come in with this one. Eventually they become other side of products, but the hydroxy group will attach on the other side, like it did before with the halogenation. Alrighty. Can I move on? You good? Okay. So, okay. The halogenation. Okay, so let's try to do. Okay. I'll just stop here today. I think.